Hello viewers, my name is Dr. V.K. Ajay Kumar, Associate Professor in the Department of ECE from Institute of Aeronautical Engineering, Hyderabad. And today we are going to discuss the topic ground wave propagation and the space wave propagation. Today's topic is about the ground wave propagation and space wave propagation, so which comes under the course Antennas, Waves and Propagation in the 5th semester. And let us now start our session. So ground wave propagation. So in the previous session, we have discussed about the different modes of propagation. So, whenever the electromagnetic waves are propagated into free space, they travel to the destination point in different paths. These paths are known as the modes of propagation. Some waves travel over the surface of the earth. Some waves travel at the distance of about 10 kilometers above the surface of the earth. Some waves will reflect from the ground and travel towards the destination point, that is the receiving antenna. So like this, different waves travel in the atmosphere at different heights, and finally they are going to reach to the receiving antenna. Here, whichever the waves that are propagated over the ground, those waves we call it as ground wave propagation. So the ground wave propagation, there are three types of propagation. One is ground wave propagation, the space wave propagation, and also the sky wave propagation. So let us today discuss about the two propagations. One is the ground wave propagation or surface wave propagation. Here, ground wave propagation, it is very important in the low frequency and the medium frequency portion of the radio spectrum. So we can transmit the signals only low frequency signals, that is around the range of 3 to 30 kilohertz or up to the range of 2 megahertz. Up to the range of 2 megahertz signals only, we can propagate the frequencies over the ground wave propagation. So the ground wave radio propagation is used for local radio communication coverage, especially by radio broadcast stations that require to cover a particular locality. So ground wave propagation is used, we are having for low frequency signals and also for short range communication. That means within a short range of communication where the requirement is the requirement of the population is very less. In that particular area, we can use this ground wave of propagation. So the ground wave radio signals is ideal for relatively short distance propagation. You can see here, one is the major advantage is short distance communication, and another one is the low frequency and medium frequency portion of the radio spectrum. As shown in the figure, you can see here. Here, suppose if we say here there is a transmitting antenna, and if there is a receiving antenna, the earth is never flat or curved. So we know that the earth is not flat, the earth is not curved. So if the earth is curved, then what happens? The transmitting antenna will transmit the signals over the surface of the earth. They touch the surface of the earth, and also they reach to the destination. The reflected wave after touching the surface of the earth, they are going to reach to the receiving section, the receiving antenna. And at the same time, some waves are going to travel like this directly, and some waves will reflect from the ground and going to reach to the receiving antenna. So these are known as the direct wave, and this is known as the ground reflected wave. So the waves which travel over the surface of the earth, we call it as a surface wave, or we can also call it as a ground wave. So the waves which travel over the surface, we call it as a surface wave, or we can also call it as a ground wave. And some waves are going to travel over the free space towards the receiving antenna. So why we are going to use this ground wave propagation? In what way this ground wave propagation is useful? Here you can see here, the first advantage of ground wave propagation is for low frequency signals. The second major advantage is it is used for short range communication only. The first one you can see here. Suppose let us say here there is a transmitting antenna. As we know that C is equal to F lambda. We know that C is equal to F lambda, and F is equal to C by lambda. F is equal to C by lambda. It means that the frequency and the wavelength are inversely proportional to each other. The frequency and the wavelength are inversely proportional to each other. Suppose if I say there is a distance of the distance between the transmitting antenna and the receiving antenna. This is the transmitting antenna and this is the receiving antenna. Here, the distance between the receiving and it is 10 kilometers. Let us say the distance is 10 kilometers. If let us say the frequency is a high frequency signal, if we are transmitting in a high frequency signal, that means at least a range of 5 megahertz or 10 megahertz, a signal is being transmitted, high frequency signal is being transmitted from the transmitting antenna. So if the frequency is very high, we know that the lambda value will be very less, as frequency and wavelength are inversely proportional to each other. So if the frequency is very high, then the value of the lambda will be very less. So as the value of the lambda is very less, so more number of waves will travel from source to the destination, from the transmitting antenna to the receiving antenna. So here what you can see here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total there are 12 number of waves are there. There are total 12 number of waves are there between the transmitting antenna and the receiving antenna, whose frequency is about 5 megahertz or 10 megahertz. A high frequency signal is being transmitted. We can see here, as many waves are propagating over the surface of the earth, the more amount of energy will be absorbed by the ground. It means that as the distance is increased, and at the same time, if more number of waves touch the surface of the earth, more number of waves are absorbed by the surface of the earth, and some amount of energy, there is some amount of loss of energy, and the remaining amount of energy is going to reach to the receiving antenna. That means here only 50% energy is being absorbed by the earth, and the remaining 50% of the radiation is being transferred to the receiving antenna. This is the case for a high frequency antenna. This is the case where a high frequency signal is sent. Suppose if we send a low frequency signal. We'll see here, if this is the transmitting antenna and if this is the receiving antenna. So low frequency is C is equal to F lambda. We know that C is equal to F lambda and F is equal to C by lambda. That means F and lambda are inversely proportional to each other. So for the low frequency signal, the value of lambda will be high. If F is less, then the value of lambda will be high. Lambda means the wavelength. So you can see here, if the low frequency signal is applied, suppose the signal is 2 megahertz, then the waves go like this. Here there are total how many number of waves are there? There are 4 waves are there. 1, 2, 3 and 4. So there are 4 waves are propagating between the transmitting antenna and the receiving antenna. It means that in the earlier case, in the high frequency signal is sent, more number of waves are touching the surface of the earth. Here there are 4 waves only, so there is a probability that less number of waves will touch the surface of the earth. As less number of waves touch the surface of the earth, less amount of energy is being absorbed by the earth. Hence, a low frequency signals only we can propagate through the ground wave propagation. Hence, low frequency signals only can be propagated to the ground wave propagation. If high frequency signal is propagated, more loss of energy takes place. Only 50% of the energy will be reached to the receiving antenna from the transmitted radiated power. And the second advantage, it is used particularly only for a short range communication only. That means, suppose if I say here, this is the transmitting antenna and if this is the receiving antenna. If we send a low frequency signal, suppose if I send a low frequency signal, here, if a low frequency signal is sent, then the transmission of radio waves is propagated from the transmitting antenna to the receiving antenna like this. If the distance between these two increases, that means let us say this distance is 10 kilometers. Here there is a distance of 10 kilometers, and we know that here there are 2 portions, A and B. These 2 portions are touching the surface of the earth, and there is a loss of energy happening between the transmitting antenna and the receiving antenna for a distance of 10 kilometers. It means that for a distance of 10 kilometers, if we send 100% of radiated power from the transmitting antenna, only 50%, only 50% is being received by the receiving antenna. 50% of the energy is being received by the receiving antenna. Let us say if the distance is increased from 10 kilometers to 20 kilometers, the distance between the transmitting antenna and the receiving antenna is increased from 10 kilometers to 20 kilometers. As the distance is increased, more number of waves will touch the surface of the earth. And ultimately, this 50% will be reduced to 25%. That means for a distance of 10 kilometers, 50% of energy is being absorbed by the earth. And after 10 kilometers also, more number of waves are going to touch the surface of the earth. And some amount of energy is being absorbed by the earth. The ground is going to attenuate the transmitted signal. Attenuation takes place by the surface on the surface of the earth. Hence, the remaining portion of the energy is being transferred to the receiving antenna. That means, for a distance of 10 kilometers, only 50% energy is being received. And again, if we increase the distance between the transmitting antenna and the receiving antenna, only 25% of the energy, only the 25% of the energy is going to reach to the receiving antenna. So as the distance increases again from 20 to 30 kilometers, as the distance increases from 20 to 30 kilometers, we are going to receive only 5%. We are going to receive only 5% of the energy from the transmitting antenna to the receiving antenna. And finally, as the distance increases, as the distance between the transmitting antenna and receiving antenna increases, none of the power is going to receive to the receiving antenna. Why? Because all the energy radiated by the transmitting antenna is absorbed by the surface of the earth. Hence, the power absorption by the receiving antenna becomes zero as the distance between the transmitting and the receiving antenna is increased in the ground wave propagation. Hence, whenever we are going to use the low frequency signals in ground wave propagation, the range of communication is limited. The range of communication is limited. We cannot transmit the low frequency signal for larger distance communication purposes, for longer distance communication purpose. So these are the two aspects which we can see here in the ground wave propagation. One is the low frequency signal. The other one is the short range communication. The other one is the short range communication. So you can see here, the ground waves are limited to very low frequency signal. So high frequency signal, if we send, more number of waves are produced, more amount of absorption takes place. More amount of absorption takes place, only 50% of the energy is being reached to the receiving antenna. Ground waves lose power with surface material and composition. So earth is never flat, earth is never curved. So some areas the earth will be flat and some areas the earth will be curved. Or some areas the earth is smooth, or some areas the earth will be very rough. So it depends upon the material and the composition of the surface of the earth, that is the loss of power. So the loss of power depends upon the composition of the material over the surface of the earth. So the ground waves are also used for a short range communication. So as the distance is increased, more amount of energy is absorbed by the ground. Hence the final received power of the receiving antenna becomes zero as the distance is increased. As the distance is increased with the transmitting antenna and the receiving antenna, finally the receiving antenna output becomes zero. That means a zero amount of power is reached to the receiving antenna. A ground wave radio signal is made up of a number of constituents. There are many number of constituents are present on the ground wave. So the loss of power depends upon the number of constituents over the surface of the earth. If the antennas are in the line of sight, then there will be direct wave as well as the reflected signal. So as we can see here, if this is the transmitting antenna and if this is the receiving antenna, if the line of sight means there is no any obstacle between the transmitting antenna and the receiving antenna, then a direct path is established between the transmitting antenna and the receiving antenna. This direct path we call it as a line of sight signal. This is known as the LOS path or LOS signal, which simply we call it as a line of sight signal. So here you can see here, this is the transmitting antenna and this is the receiving antenna. If the direct path is established, if there is no any obstacles between the transmitting antenna and receiving antenna, and this direct signal we call it as LOS signal, or direct path we call it as line of sight path. So as the name suggests, the direct one is the one that travels directly between the two antennas and is not affected by the locality. So it is not affected by the locality means it is not affected either by the trees, by the hills, or by the mountains, or by the any obstacles between the transmitting antenna and the receiving antenna. So there will also be a reflected signal, as the transmission will be reflected by a number of objects, including the earth surface and hills and large buildings. So whenever a wave is propagating between the transmitting antenna and the receiving antenna, there is a possibility that these waves will reach to the destination directly, and some waves will strike the surface of the building and reach to the destination, and some of the waves, the radio waves, are going to touch the surface of the earth and going to reflect back to the receiving antenna. So this is known as the LOS or direct path, and this is known as the reflected path. Here we can observe that the same radio wave signal is going to take three different paths to reach to the destination, that is the receiving antenna. So here this is the direct path, this is the ground reflected path, and some waves are going to strike any obstacles over the surface of the earth or in the free space and going to reach to the receiving antenna directly. So these electromagnetic waves are going to reach to the receiving antenna in different paths. Hence, there will be some delay in receiving the signal at the receiving antenna. All the field strengths reach to the receiving antenna. We need to integrate all the electric field strengths reached to the receiving antenna, so that we can calculate directly the amount of power received at the receiving antenna by calculating by the summation of all the electric field strengths received at the receiving antenna. The radio wave signal spreads out from the transmitter along the surface of the earth. The radio signal spreads out from the transmitter along the surface of the earth. Instead of just traveling straight line, the radio signals tend to follow the curvature of the earth. So just now I told you that the earth is never flat, the earth is never curved. It's just the radio signal, it follows the curvature of the earth. It follows the curvature of the earth. This is because the currents are induced in the surface of the earth, and this action slows down the wavefront in this region, causing the wavefront of the radio communication signal to tilt downwards towards the earth. So whenever there is a curved earth, whenever the electromagnetic wave signal is going to propagate from the transmitting antenna to the receiving antenna, here some waves are induced here. Some waves are induced over the surface of the earth, and here there is some action is taking place. That is, action of reflection is going to take place at this point A, and also as the curved surfaces are more, there will be multiple number of reflections are going to happen here. Multiple number of reflections are going to happen, and finally the wave is going to reach to the receiver. That means the radio wave signal here, you can see here, it is going to follow the curvature of the earth. It is going to follow the curvature of the earth from the transmitting antenna to the receiving antenna. So with the wave front tilted in this direction, it is able to curve around the earth and be received well beyond the horizon. So whatever may be the surface of the earth, it may be flat or curved, the transmitted signal, it just follows the curvature of the earth. That is, it will be traveling by over the surface of the earth beyond the horizon also. Beyond the horizon, and it will be traveling in the free space towards the receiving antenna. The type of antenna and its polarization has a major effect on the ground wave propagation. So always, whenever we are going to transmit the signal from the transmitting antenna to the receiving antenna, so we need to check before sending the signal whether the antenna is polarized vertically or horizontally. So the polarization means the orientation of electric field vector with respect to the surface of the earth. We call it as polarization. You can see here, suppose this is the electric field vector here, and this is the surface of the earth. If the electric field vector is perpendicular to the surface of the earth, then we call it as the vertical polarization. Then we call it as a vertical polarization. If the electric field vector it is in the direction of parallel to the surface of the earth, this is the surface of the earth. If the electric field vector it is parallel to the surface of the earth, then we call it as horizontal polarization. Then we call it as a horizontal polarization. So always a vertical polarization is preferred over horizontal polarization. Always the vertical polarization is preferred over horizontal polarization. You can see here the vertical polarization, the electromagnetic waves are propagating directly from the transmitting antenna to the receiving antenna. They are not going to touch the surface of the earth. But when we locate the antenna horizontally with respect to the surface of the earth, you can see here, if this is the antenna here, a dipole antenna, this dipole antenna is placed vertically with respect to the surface of the earth. Hence, the electromagnetic waves are going to travel directly. They are not going to touch the surface of the earth. Suppose this is known as vertical polarization. Suppose if we use the horizontal polarization, suppose the antenna is, this is the antenna, this antenna is placed horizontal. This antenna is placed horizontal, then the electromagnetic waves radiated by this antenna will touch the surface of the earth. Will touch the surface of the earth. That means some amount of rays are going to free space, some amount of rays are going to touch the surface of the earth. That means there is more amount of loss of energy with horizontal polarization than vertical polarization. In vertical polarization, all the electric field vectors are going to radiate in free space and going to reach the receiving antenna directly. But in the case of horizontal polarization, you can see here, when the antenna is placed in parallel to the surface of the earth, some amount of energy is being absorbed by the surface of the earth. Hence, only half portion of the energy is being radiated into the free space. Half portion is going to radiate into the free space. Hence, this is the reason why always the vertical polarization of antenna is preferable than horizontal polarization of the antenna. And we need to see that the transmitting antenna and the receiving antenna both must be, the polarization must be same. If the transmitting antenna is vertically polarized, then the receiving antenna must be vertically polarized. So then only more amount of absorption takes place. Suppose if we place the transmitting antenna vertically and if we place the receiving antenna horizontally, see here, this is the transmitting antenna and this is the receiving antenna. This is the receiving antenna. This is vertically polarized and this is horizontally polarized. When only the electromagnetic waves are radiating from the transmitting antenna to the receiving antenna, only less amount of energy is being absorbed. Only less amount of energy is being absorbed by the receiving antenna. Total amount of energy, some loss of energy is going to take place. Hence the power absorption will be very less. Hence only 50% of the signal will be absorbed by the receiving antenna if the antenna is horizontally polarized. We need to check that before transmitting the signal, both the antennas are vertically polarized or not. That is, the broadcast stations must be use vertical antennas only, but not horizontal antennas. How we are using the horizontal antennas, the signal will be transmitted directly to the surface of the earth. No signal goes into the free space. This is our standard equation to find out the electric field strength. The electric field strength that is going to receive at the receiver, it depends upon the height of the transmitting antenna, the height of the receiving antenna, the source induced current, the wavelength, and also the distance between the transmitting antenna and the receiving antenna. So these are the five important parameters which where the total electric field strength is calculated based upon the height of the transmitting antenna, based upon the height of the receiving antenna, the amount of current of induced the signal that is radiated by the transmitting antenna, and also the distance between the transmitting antenna and the receiving antenna. So the total electric field strength at the receiving antenna is calculated by this formula 120 by HT IS by lambda D. The field strength of the signal at a distance from the transmitting antenna due to the ground wave can be obtained by E is equal to 120 by HT IS by lambda D. 120 by HT IS by lambda D. The ground wave, another expression, the ground wave field strength, whenever we are using the ground wave propagation, suppose if the electric field strength we are going to calculate on the surface of the earth, then this formula is used, that is Eg is equal to E naught A by D. Eg is equal to E naught A by D. Let us see the attenuation characteristics for the ground wave propagation. Attenuation characteristics for the ground wave propagation. So according to the Sommerfeld, the scientist, for a flat earth, the field strength of a ground wave propagation is given by Eg is equal to E naught A by D. According to the Sommerfeld, for a flat earth, the field strength for a ground wave propagation is given by the Eg is equal to E naught A by D. Eg is equal to E naught A by D. Here, where E naught is the ground wave field strength at the Earth's surface at a unit distance without considering the Earth losses, and Eg is the ground wave field strength. E naught is the ground wave field strength at a unit distance without considering the Earth losses. A is the attenuation factor accounting for Earth losses. The attenuation factor depends upon the surface of the Earth, whether the surface of the Earth is flat or curved, whether the surface of the Earth is smooth, whether the surface of the Earth is rough. So the attenuation factor depends upon the these parameters, whether the Earth is rough or smooth. And D is the distance between from the transmitting antenna to the receiving antenna. The electric field strength at a unit distance between the transmitting and the receiving antenna is given by 300 into root P volts per meter. 300 root P volts per meter. So for a vertical antenna which is non-directional in the horizontal plane, the radiation field produced is proportional to the cosine of angle of elevation. So then the field at a distance given by E naught is equal to 300 root P volts per meter. So P is equal to radiated power in kilowatts and D is equal to distance in kilometers. So E naught is equal to 300 root P volts per meter, where P is the radiated power in kilowatts, D is the distance in kilometers. And here the attenuation factor A depends upon the frequency, the dielectric constant, and also the conductivity of the Earth. So the attenuation factor A. So we know that Eg is equal to E naught A by D. Eg, we know that Eg means ground wave field strength is equal to E naught A by D. So this, what is A? A represents the attenuation factor. This attenuation factor depends upon three parameters. One is the frequency, the other one is the epsilon, that is the dielectric constant, and also sigma, that is the conductivity of the Earth. So F, epsilon and sigma. So these three are the parameters on which the attenuation factor A depends. So for analytical purpose, it is expressed in terms of two auxiliary variables such as numerical distance P and phase constant P. So we can also represent A in terms of two auxiliary variables which we consider as small p and small b. We consider as small p and small b. So here the attenuation factor is expressed, sometimes it is expressed in terms of two auxiliary variables, that is small p and small b. So we define these two variables p and b by some expressions here. So these two variables are determined by frequency, distance and dielectric characteristics of the ground as conductor for radio frequency and are given as follows. So these two variables are determined by the frequency, distance and the conductivity of the Earth. So there are some equations here. Attenuation factor depends upon two auxiliary variables. We have seen that we want to find out the value of A. This is the formula to be used here. 2 plus 0.3 P by 2 plus P plus 0.6 P square. So this is the actual formula to find out the attenuation factor. And where P is given by 0.582 into D in kilometers F square by sigma. The distance between the transmitting and the receiving end is expressed in terms of kilometers, and F, the frequency, is expressed in terms of megahertz, and the value of P, the auxiliary variable, is given by 0.58 D into F square by sigma. And we can also represent the exact value of P by another expression, that is P is equal to pi by x into d by lambda into cos B. So for a vertically polarized antenna, so these are the formulas applicable only for vertically polarized antenna. As we have seen that Eg is equal to E naught A by D. Eg is equal to E naught A by D. And A is equal to, we have seen that 0.2 plus P square. Here 2 plus 0.3 P by 2 plus P plus 0.6 P square. And we can find out the value of P only when the transmitting antenna is vertically polarized. So P is equal to pi by x d by lambda cos B, and B is equal to tan inverse of epsilon r plus 1 by x, epsilon r plus 1 by x, and where x is given by 1.8 into 10 power 12 by f into sigma. So x is given by 1.8 into 10 power 12 sigma by f mho per centimeter. We can also represent in terms of meters as 1.8 into 10 power 4 by f sigma mho per meter. So these are the equations to find out the value of Eg, that is E naught A by D, where A is equal to 2 plus 0.3 B by, we have seen the formula P square, and where P is given by pi by x d by lambda and cos B, where B is equal to tan inverse of epsilon r plus 1 by x. Epsilon is the permittivity, and x is given by 1.8 into 10 power 12 by f mho per centimeter. So these are the formulas related only for the vertical polarization only. And if the wave is horizontally polarized, if the transmitting antenna is horizontally polarized, then the value of P is given by pi dx by lambda into cos B. We can write as pi dx by lambda into cos B, where B is one auxiliary variable given by 180 degrees minus B1, or B1 is equal to tan inverse of epsilon r minus 1 by x. You can also write as B1 is equal to tan inverse of epsilon r minus 1 by x. So these are the formulas. P and B represented only when the wave is horizontally polarized. The roughness of the earth. So as we have seen that in the ground wave propagation, the electromagnetic signal that is going to transmit between the transmitting antenna and receiving antenna depends upon the frequency, depends upon the dielectric constant, depends upon the conductivity of the earth. So all these three parameters depends upon the roughness of the earth, whether the earth is rough or whether the earth is smooth. So the reflections of electromagnetic waves vary with the nature of the earth, whether the earth is smooth or rough. So earth is classified as smooth or rough. So according to the Rayleigh criterion, it's a common tool for estimating the degree of electromagnetic roughness of a considered surface of the earth. So it is a common parameter to find out the roughness of the earth, where Rayleigh criteria is given by R is equal to 4 pi sigma s into sin theta I by lambda, where R is equal to 4 pi sigma s sin theta I by lambda, where sigma s is the standard deviation of the surface irregularities related to the mean surface height, and theta I is the angle of incidence measured from the surface of the earth, and lambda is the wavelength. So R is given by 4 pi sigma s sin theta I by lambda. And according to this expression, we are going to find out the value of R. Based upon this formula, we are going to find out the value of R. Suppose if the R value what we got is less than 0.1, then the earth is considered as smooth. Then if the R value is less than 0.1, then the earth is considered as electrically smooth. And if the value of R is greater than 10, then the earth is considered as electrically rough. So based upon the formula, that is the value Rayleigh criterion, R is equal to 4 pi sigma s sin theta I by lambda d. So 4 pi sigma s sin theta I by lambda gives the Rayleigh criterion of roughness of the earth, that is R value. If R is greater than 10, the earth is considered as rough. If R is less than 0.1, then the earth is considered as electrically smooth. And wave tilt. So wave tilt, it is defined as the change of orientation of vertically polarized ground wave at the surface of the earth. So this occurs due to the diffraction. So due to tilt, both horizontal and vertical components of the electric field exist and are not in phase. So when I'm going to transmit a signal from the transmitting antenna to the receiving antenna, if there is any obstacle here, the wave is going to strike any obstacle. It changes its polarization. That means the wave is going to reflect multiple reflections are going to happen when it strikes the obstacles. This occurs due to the diffraction. That means a vertical polarized wave it may become a horizontal wave. That means the electric field vector direction changes here. when it strikes the obstacle. So suppose electric field is in this direction. After striking the obstacle, the electric field direction changes. It's going to change the direction. So the change of orientation of the vertically polarized ground wave at the surface of the earth, we call it as the wave tilt. We call it as the wave tilt. The change of orientation of vertically polarized ground wave at the surface of the earth, we call it as a wave tilt. So this occurs due to the diffraction. So due to the tilt, both horizontal and vertical components are not in phase, and also the electric field component also, magnetic field components also, they both change when reflection, multiple reflections are going to happen after when strike the obstacles. So wave tilt also depends upon the conductivity and the permittivity of the earth. This supplies sufficient power to the earth over which the wave can be easily passed. So vertically polarized wave forward tilt is observed at the surface of the earth. So by how much amount the wave tilts, it depends upon the conductivity and the permittivity of the earth. So this is a formula to find out the wave tilt. Z is equal to root of omega mu by sigma square plus omega square epsilon square under root. Angle half into tan inverse of rho by omega epsilon. So this is, let us end the session here. What we have seen today is about the wave tilt, about the roughness of the earth, and also about the ground wave propagation. So these are the references. That is antennas on wave propagation, which we have the session. In this session, we have seen the content was seen in the references antennas on wave propagation. That is Bakshi and K.D. Prasad. And you can also refer the references like Balanis and also John D. Cross. So for the ground wave propagation, you can also refer these textbooks, either Bakshi or K.D. Prasad or Balanis and John D. Cross. Let us end the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.